Hi students, today I will demonstrate you how to do the experiment Zener IV characteristics. The major difference between a Zener diode and a PN junction diode is the doping concentrations. Zener diode is heavily doped diode, whereas ordinary PN junction diode is normally doped. Means that in doping the concentration, if you add one impurity atom to the 10 to the power 10 mother silicon or germanium atoms, that doping gives you ordinary junction diode. If you increase the doping concentration, suppose say for 10 to the power 6 mother atoms, if you add one impurity atom, then we will get a Zener diode. The other important difference between ordinary junction diode and Zener diode is there is a sharp breakdown in Zener diode in reverse bias. You need to operate Zener diode in reverse bias under breakdown only. There are different mechanisms to explain this breakdown in reverse bias of a Zener diode, like avalanche multiplication and Zener breakdown. You will discuss all this in the theory class when you have semiconductor physics class. Let us look how to connect the forward circuit to draw forward characteristics of a Zener diode. I told you that this is the symbol for Zener diode and this is actually the Zener diode. And we have to connect an ammeter here. So I am taking the positive marked terminal and connected to the positive of the milliammeter. And I am taking another terminal here and connecting to the second terminal of the milliammeter. Then we have to add here the voltmeter. I am now connecting positive marked terminal to positive of the voltmeter here. You see it. And negative to the negative of the voltmeter which was marked here. Now we have to give power to the circuit. Therefore, I am adding a DC power of 0 to 3 volts, which is a variable one from 0 to 3 volts. I am taking positive and connecting to the positive terminal of the battery, which is a DC source. Negative marked terminal to negative of the source. You can see that this is a variable potentiometer. By rotating this, you can change the voltage. If you change the applied forward biased voltage, the current through the circuit also changes. This knob is to switch on or switch off the power. So while doing the connections, don't switch on the power. And also we have two ranges to be selected for an ammeter and also voltmeter. If I select this switch, say upwards, it measures 0 to 30 milliamperes. If I go down, it measures up to 300 microamperes. Similarly, the voltmeter also is having two modes. If it is upwards, then it measures 0 to 1, and if it is downwards, it measures 0 to 1. This setup is required because we are using 0 to 3 volts for forward bias and 0 to 10 volts for reverse bias. In forward bias, the Zener behaves similar to ordinary junction diode. When it is under forward bias, it gives a current in milliamperes for a applied voltage. But Zener diode shows a remarkable property in reverse bias when compared to ordinary diode. Now I am taking readings in forward bias condition. Now we have done everything, making all the connections. I am selecting 0 to 300 amperes range. Therefore, you need to measure the readings from the top scale, because top scale in milliampere starts from 0, 5, 10, 15, 20, 25, 30. That is the maximum one. And also when coming to the voltmeter, you keep in 1 volt range, and you see you have to read the top scale only 0, 2, 0, 0.2, 0.4, 0.6, 0.8 and 1 is the maximum range. So you have to now read the readings from the voltmeter and also from the milliammeter using only top scales. Okay, because we have selected the ranges from 0 to 1 volt for voltmeter and 0 to 30 milliamperes for milliammeter. Now I switch on the power, okay, so that the power is come, and here you see this is connected to the power supply, AC power supply, and we have a rectifier inside the board which converts AC into DC, and we are again applying DC voltage. Now slowly I'll change the current, voltage, and note down the current value. Initially the value of voltage is 0. I am noting down in the tabular form as forward biased condition. So it is 0, I am writing here 0 voltage, and I also keep the current value also 0. So this is 0, this is 0. Now we will go and see, change this knob to change the voltage. Now I am slowly adjusting this knob so that it will go a value of it. But you see that it is 0 to 0.2. There are 10 divisions from 0 to 0.2. So each division you have to calculate how much it is. So 0.2 divided by 10 divisions is 0.02 for each of these divisions. Therefore, if I move, suppose say 2 divisions, it is 0.04. Now I am setting this value to conveniently about here, which is 0.1. So if I note down the 0.1 voltage, I will look at the current value. Current value is 0, there is no change. So I write the current value in the ammeter as 0. Now I set again the value of the voltage, input voltage, by changing this knob and carefully looking the voltmeter. So voltmeter readings, I slowly change it and I keep it at 0.2. So I note it down to 0.2, and the value of current is still it is 0. I write 0 value only, and slowly increase this to maybe 0.3. I will just to 0.3. So the value is 0.3 for voltage, and the current is again 0. You make a note of that, and increase the current further to voltage to 0.4. So if I keep the voltage as 0.4, the current value is still 0, so I put 0 only. Then now I increase this to 0.5, and the current is 0. Now I go on increasing this value to 0.6. I go on to 0.6. Okay. So current is still 0. Now I increase this to 0.7. Yeah, current started moving, you see it. 0.6 I have here, up to that it is 0. But if I increase to 0.07, the current has increased, and you have to read the reading from the top scale. Therefore top scale is 0 to 5, it is around 2.5. Therefore, I take for 0.7 volts of input voltage across the diode, I note down the current value as 2.5 milliamperes. Now I go on increasing the voltage by 2 more divisions. Okay. So if I increase the 2 more divisions, see that I have not adjusted to 0.8, only 1 division. It is 0.7, it is 0.72 only, and the current value is 5. So I am writing this value as 0.72 and noting down current as 5 milliamperes. So as you are approached the cut-in voltage of a forward biased diode, when it is a Zener diode or it is an ordinary junction diode, we have a cut-in voltage. Once you reach the cut-in voltage, even the applied input voltage is increased, the voltage across the diode remains constant. Thereby, the change is very small, but current is increasing largely in the forward bias also. Now look at this. I'm still changing the value of the input voltage. Okay, one more division. Then it will be 0.74 is the input voltage. And the current has raised to 12.5 milliamperes. So I note down this value. And I further increase the voltage slowly, and you see that it has gone to 0.8, but there is a lot of increase in the current as 17.5 or 18 I can note down. So applied voltage is a little lower than 8, I'll write 0.78, and I note down the current value as 17.5 amperes. Finally, I'll take one more reading and increase it. See, it is not further increasing, it is 0.7 only, 0.8 only, and the current is around 22. I say now the value as 0.8 and the current value is 22 milliamperes nearly. I stop taking readings here and I will show you the readings, and you enter these readings in your record book, because we have to draw a graph for these readings. If you want to draw a graph for this, I am showing how to draw a graph. You have seen already that this behavior in the forward bias of a Zener diode is quite similar to ordinary junction diode. Now I take on x-axis voltage across the diode and a current in the circuit I. This is in milliamperes and this is in volts. So starting from 0 up to maybe I'll take on this as 0.2, 0.4, 0.6, 0.8, something like this. And I note down the corresponding values to plot the graph. Up to 0.5 there is no current, but after that the current started increasing, and it has gone to maximum like this. And this is the linear region. You know that diodes are non-ohmic devices. Resistance is a ohmic device. That means there is a linear relationship between the applied voltage and the current in resistance. But here there is no linear relationship between I and V. It is an exponential relationship. But if you want to apply Ohm's law, you have to select the region in which the curve is almost a straight line. Is almost a straight line means that you can apply Ohm's law here, treating it as a linear device. So I choose two close points like this and draw perpendicular to x-axis and also y-axis. And this difference I call it as delta V, and this difference I call it as delta I. That means for a small change in voltage, I would like to calculate how much change is there in the current. So therefore, if I write this one, this is nothing but change in current. In terms of axis, it is difference of y coordinates. This is difference of x coordinate. You defined slope as difference of y coordinates by difference of x coordinates. Therefore, if I write slope here, I'll get delta I by delta V. But from Ohm's law, V by I is the resistance. Therefore, if I take 1 by slope, I get this as V by I, delta V by delta I, which you are able to find out the resistance in forward bias of a Zener diode. But look at here, when you are taking the readings, you have taken voltage in volts, but current is in milliamperes. Therefore, while doing the calculation, you need to convert this current I into amperes. Therefore, if I write delta V by delta I in amperes, I write 10 to the power minus 3 because we have taken this as milliamperes. Thereby, you calculate the forward resistance of the Zener diode, whose characteristics are similar to ordinary junction diode. Now we will do reverse bias experiment. I have removed all the connections from the forward biased condition. I switched off it And now you connect, this is the Zener diode and this is the negative part which has gone to positive of the battery, and this is the positive side of the diode which has gone to negative side of it. Therefore, the Zener diode is under reverse bias. I add the ammeter between the two terminals, connect positive to positive, and I take the negative terminal. These are the connecting wires we are making the connections. So here you need to add voltmeter. I take the voltmeter from these two terminals and add the voltmeters like this. Now we have to connect the DC supply. The DC supply is 0 to 10 volts. You need to add here. We have 0 to 10 supply here. Therefore, I take positive of this connected to positive of this, but this positive has gone to negative of the diode. Therefore, it is in reverse bias. And I am connecting negative of this one to negative terminal of the source. Now we have to change the meter ranges. As it is reverse bias, the current is small and it is in microamperes. Switch this to 0 to 300 microvolts range. Similarly, as you are applying higher voltage up to 10 volts, you have to change this to 10 volts. And remember that as you are in 0 to 300 microamperes for the ammeter, you have to use the bottom scale or the second scale, because second scale is from 0, 50, 100, 150, 200, 250 and 300. So you should take the readings from this scale only, lower scale only. And coming to the voltmeter also, we switch it down to 10 volts range. As we have switched it to 10 volts range, you need to take the readings from the lower scale, because the lower scale is from 1 volt, 0, 2, 4, 6, 8 and 10 volts. So I now switch on the power supply. Here I am getting power and I need to change this. And this is the tabular form for the reverse bias. Reverse bias, I have taken the tabular form, voltage in volts and current in microamperes. So we start doing the experiment and note down the readings. Initially, I say the voltage applied or the voltage across the diode is 0. So I note down 0, and the current is also 0. I make a note of zeros here. Now see the reading. For 0 voltage, we have 0 current. I will now change the voltage slowly and note down the corresponding values of current. When I am changing it, see that I have changed the voltage to 1 volt. This is 1 volt because this is 2 volts. Lower scale I am reading it. As it is 1 volt, I note down it as a 1 volt and look at the ammeter. Ammeter is showing only 0. So I put only 0 here. Then I change this value to 2 volts. I am going to 2 volts here. See the 2 volts adjusted in the voltmeter and the current is still 0. So I note down for 1 as 0 current. Now I'll just increase it to 3 volts. I am slowly increasing this and see that the meter is changing and it is moving to 3 volts. And respectively, the current what we have seen is also 0. So we note down the value to 0, 3 also 0. Now go to 4 volts. So I have adjusted to 4 volts. But the current is still 0. So I note down 4 volts also 0. Now I go for 5 volts. And still there is no change in the current. It is at 0 only for our meter. So I note down 0 for current value. And I move on slowly to 6, and we can see there is maybe a small change, but not significant to observe it. Hence, I am writing it as a 6 also, 6 volts voltage also, a 0 value of it. Now we will go on further increasing it very slowly. As I am increasing this slowly, okay, very slowly I am increasing it. Now for 6 volts of voltage across the diode, we have got 0 current in this. I now slowly increase the input voltage to 6 point, see this here, okay. So from the bottom scale it is 6.4. So I am writing it as 6.4, I am writing current as 0. Now I slowly increase this and see whether there is a change in the ammeter or not. I am going slowly increasing it. Yeah, there is a small change in it. Now look at this, it is 6.8 volts. And the corresponding current value is nearly 50 microamperes. So I am writing this as 50 microamperes. Now I change the voltage further and see that there is no change in the voltage, but still the current is increasing, so to 10 microamperes. Hence I write the value as 6.8 only as voltage and the current value as 100 microamperes. That's why 6.8 I am getting 100 microamperes. Now move this to further. Even I am changing the knob, there is no further much change in the voltage. Now it has moved to 0.7 and the corresponding value has gone beyond the meter reading. Therefore I slowly decrease it and I see that here, okay, 200 for 7. So 7.0 volts of in voltage across the diode, current is now 200 microamperes. Now if I further change it, this, I am turning this, but there is no change in the voltage, but see the current has increased near to above 250, 275, something like that. So thereby I am taking the final reading as 7 volts, but the current is around 280 microamperes, roughly I am telling. Yes? So we have to draw a graph. Now look at this. When I draw a graph in the reverse bias, I am taking third quadrant, because as it's a reverse bias, voltage is negative, therefore I am taking here, and current is also negative. But current is in microamperes, as it's a reverse current, I am taking it as a negative. And here voltage in volts. I have changed the voltage from 0 to 7 volts, something like this. And we have noted down the corresponding current values. See that up to 0, from 0 to 6, the current is 0. So current value is 0. If I take 0, this is 0, 2, 4, 6, 8, 10. The current is 0 up to 6, there is no current. And even 6.4, there is no current. But once I moved to 6.8, there is a sudden and sharp increase in the current, whereas voltage is almost remained constant. Hence, here I'll come it and the current has increased up to, maybe if I take as 20, 40, 60, 80, something like this, 100. If I just keep it, I may have 300 here. Then the current has increased sharply. This is the second major difference between the junction diode and a Zener diode. In The beginning of the video we have seen that the major difference between a junction diode and Zener diode is the doping concentration levels. And second most practical application is there is a sharp breakdown in a reverse bias wherein the current sharply and suddenly increases once you reach a certain voltage. The certain voltage is now called as Zener breakdown voltage Vz. Now in reverse bias we will find the breakdown voltage of the given diode. If I plot a tangent to this curve where it is exactly touching, that will be the Zener breakdown. Now it is around 6.8. So Vz we found from the experiment as 6.5 volts nearly. Hence, in breakdown region, voltage remains constant by and large, but current increases very sharply as you have seen from these values. Hence, when you operate a Zener diode under reverse bias, voltage remains constant and current increases sharply, meaning that Zener is acting as a regulated power supply, giving a constant voltage despite of the current is increasing. This is the major application of a Zener diode. Thereby, you should remember two important differences between an ordinary junction diode and a Zener diode. One is the doping level concentrations. Zener is a heavily doped diode, and Zener diode has a breakdown voltage below which there is no current, above which current increases sharply but voltage remains constant. And the breakdown in a Zener diode is reversible. If you decrease the value of the applied voltage, then it becomes normal one, and it again works as if you increase the voltage and goes to breakdown. So under breakdown, voltage across the Zener diode is constant and therefore it is a constant voltage source. Hence we call it as regulated power supply. If you use a Zener diode, you can create a good regulated power supply with a constant output voltage. And remember that this breakdown occurs in the Zener diode due to avalanche breakdown and also Zener breakdown. These two mechanisms are reversible mechanisms, and the diode is not even operating under breakdown region, it is not spoiled. But ordinary diode will also have a breakdown. If you operate the ordinary diode in breakdown at higher voltages, because generally the breakdown voltage for ordinary diode is around 60 or above. If you apply 60 volts in the reverse bias for a diode, PN junction diode, it will burn out. That means it will not work further and it is completely spoiled. So you should not use ordinary junction diode in breakdown region, even though it has a breakdown. This breakdown is completely burning of the diode. And diode, this is not a reversible process in PN junction diode. But in case of a Zener diode, it is reversible, and you need to use Zener diode under reverse bias in breakdown region only. And the Zener diodes are available with different values like 4.2 Zener breakdown, 5.7, 6.8, something 9.7, 12 volts, even you have 50 volts higher values also. But these values are given by the manufacturer, and you have to see the number of the Zener diode and find out the corresponding breakdown voltage.